I want to talk a little bit more about optimization. So first, rather than me just read this to you, I'm going to have you just read it. You can pause the video and read through this information. Okay, so I do want to point out, first of all, oh, look, there's two number sixes down here. But the second number six, if you are asked to find a maximum or minimum on a closed interval, you must test the endpoints as well. So just make sure, hopefully we'll have a problem on here like that. But definitely sometimes the max or min can occur at an endpoint. So the first one I want to do is this problem. There's not really a word problem context. We've got two numbers that sum or add to 40. Find the numbers that maximize their product. Complete the chart. Now, I'm not going to tell you you always have to complete a chart, but that was one of the things in the information that sometimes it's helpful to make a chart. So here they have, they've filled in the smaller numbers. So if the smaller number is 1 and the numbers add to 40, then clearly this would have to be 39. And if we multiply 1 times 39, because we're trying to maximize the product, so we get 39. So if the smaller number is 2, then the larger number is 38. And if you multiply those two numbers, you will get 76. If the smaller number is 4, then the larger number would have to be 36. And if you multiply those, you get 144. If the smaller number was a half, then the larger number would be 39.5. And the product here, and no, I don't have these memorized, I just already did it. So 19.75. And if the smaller number were negative 10, they have to add to 40, so the larger number would have to be 50, and our product would be negative 500. Now, the whole purpose of this chart is so you can find the equation that we're trying to maximize. So if the smaller number is x, then the larger number is 40 minus x, and the product is x times 40 minus x. That's what we're trying to maximize. So I'm going to write that out. P equals, we've got, if I distribute the x, we have 40x minus x squared. Again, the whole purpose for the chart is to lead you to your equation. You might not need the chart. Maybe you can read the problem and come up with the equation that you are trying to maximize. So how do we maximize? And again, I think you have this information in there. We already have our equation. We're going to take the derivative and set it equal to 0. So that is our plan. So P prime, I get 40 minus 2x. Now I'm going to set that equal to 0 to find my critical points. So we get x equals 20. I'm going to do a little sign chart. 20 is my critical point. This is P prime. So if I pick something smaller to plug in, like say 10, then I'm going to have 40 minus 100. Well, wait. No, sorry, was plugging it into P. Don't want to do that. If I plug in a 10, 40 minus 20, we end up with a positive number. And if I plug in something larger than 20, like 30, 40 minus 60, so I'm going to have a negative. So if I want to maximize, now the reason I do the little sign chart is I want to show that it indeed is a maximum. So we've got, it's going from positive, the P prime is going from positive to negative, so that means my product is going from increasing to decreasing. So we know at 20, we have a max. So my two numbers, because don't forget to answer the question, the two numbers are 20 and 20. The max product, if you multiply those, is 400. So again, one of the things on this was be sure to answer the question that is asked. So make sure that you do answer the question. Okay, next we're asked to find two positive numbers A and B that minimizes the sum of twice A and B. So if the product of the two numbers is 288. So I've got two numbers, A and B. And you can use the chart if you want to. I'm actually going to do this one without using the chart because from the words, I know I need the sum of twice A and B. So I need 2A plus B. So this is what I am trying to minimize. I'm going to call this y equals, and I want to minimize this. Now, one of the things you'll notice in our directions was you really only want to have a single variable. So if there's more than one variable, then you need a secondary equation to relate the two variables. So that's the case here because I have two variables. So I'm told that the product of the two numbers is 288. Well, the two numbers are A and B, so the product, A times B, is 288. So you would have an option to either solve for A or solve for B. I'm going to choose to solve for B, and I get 288 over A. And then we're going to substitute this into our primary equation. So I get y equals 2A plus, and I'm going to rewrite this as 288 times a to the negative 1 power to set it up to find the derivative. So then y prime is 2, and here we'll have a minus 288 a to the negative 2, or we could write this as 2 minus 288 over a squared. Now remember what I need to do next. I need to set it equal to 0 to find my critical points. Well, in order to do that, I want to find a common denominator, so I'm going to multiply this by a squared over a squared. So we get 2a squared minus 288 over my common denominator of a squared, and I'm going to set this equal to 0. So remember, when we have a rational function and we want to find the zeros, we only have to worry about setting the numerator equal to 0. We get 2a squared minus 288 equals 0. So I'm going to add 288 and divide by 2. I get a squared equals 144. So a equals, I was going to say plus or minus 12, but if you look up here in my directions, my problem said find two positive numbers a and b. So I'm only going to consider a equals 12. So this is y prime, and my critical point is 12. So if I plug in something smaller into my derivative, like 10, then I'm going to end up with a negative on the top and a positive in the bottom, so it's going to be negative. And if I plug in something larger than 12, I'll end up with a positive on the top and a positive on the bottom. And remember, we were trying to minimize, so this shows that it is a minimum because y prime is going from negative to positive, which means y is going from decreasing to increasing. So then my two positive numbers, so the two numbers are 12 and if you substitute the 12 back in, 288 divided by 12 is 24. So those would be the two numbers. So I'm going to skip over this one. It's similar. This was the one like we did in class. Well, like on the last video I had you watch, the poster board problem. So that's similar to that. So we're going to take a look at number 5. And this is a very typical problem where you'll see something similar to this. So the problem is I am 1 mile off of the coast and wish to get to a town 3 miles down a rocky coast as shown in the figure to the right. I need to swim to the shore and then walk along the shore. At what point X should I swim to along the shoreline so that the time it takes to get to town is a minimum? I can swim at 2 miles per hour and walk at 4 miles per hour. So we're trying to figure out, okay, so if I can walk faster than I swim, where exactly should I land along the shoreline so that I could minimize my time? I want to get there as quickly as possible. So a couple things to keep in mind is distance equals rate times time. And if we switch this formula around and solve for time, we get time equals distance divided by rate. Now remember, we're trying to minimize the time, so I needed to have this involving the time. So let's have some numbers. Like what if I swam, just do, if that was south, and just swam 1 mile. So if this was 1 mile and I just swam directly here, then that means I would have to travel this distance here is 3 miles. So that means I would be walking for those. And notice the shape that I'm dealing with. So if I am going to swim, if I'm swimming that right here, then I'm going to be walking 3 miles. So that would be here. My swim time, remember it's 2 miles per hour for the swim time and 4 miles per hour for the walk time. So my swim time, remember to find the time, I take the distance divided by r. So I'm going to take 1 over 2, since my rate is 2 miles per hour. And my walk time is going to be my walking distance, which is 3, divided by 4. So if I look at my total time, I'm going to add my swimming time plus my walking time, and I'm going to get 1 1/4 hours. Okay? Now, what happens if I instead swim directly to the town? Well, if I swim directly to the town, then this distance here becomes my distance if this is the town. So this is 3 miles. This is 1 mile, clearly not drawn to scale. And notice I have a right triangle, so I'm going to use the Pythagorean theorem. So we get d squared equals 1 squared plus 3 squared. So d squared is 10, which means d is the square root of 10. And I know when you square root plus or minus, but we're talking distance, so it would have to be positive. So if I swim directly to town, then that means I'm going to travel that, that would be my swimming distance. My walking distance would be 0. My swimming time would be the swimming distance, the square root of 10, over 2 miles per hour. My walking time would be 0 over 4, which is still 0. So my total time would be the square root of 10 over 2, which is about 1.581 hours. Okay, so now let's think about, well, what if we swim to X? So then my swimming distance is going to be, well, let's think about what that would be. If this is 1 and this is X here, then my swimming distance is going to be the square root of X squared plus 1. I'm using the Pythagorean theorem. So that would be my swimming distance, the square root of X squared plus 1. My walking distance, if I land right here and that's X miles, then this what's left, this portion here, would be the total 3 minus x. So that's my walking distance. So my swim time is going to be the square root of x squared plus 1 all over 2. And my walking time is going to be 3 minus x all over 4. So my total time, I'm going to call t, is the square root of x squared plus 1 over 2 plus 3 minus x over 4. And I want to minimize this. Notice I only have, even though it's messy, but I only have one variable, so we're good on this one. So let's, I'm going to kind of rewrite this as 1/2 x squared plus 1 to the 1/2 plus 1/4 times 3 minus x. Now I want to find the derivative. So the power rule, I'm going to get 1/4 x squared plus 1 to the minus 1/2. And then I need to use the chain rule, so I'm going to have times 2x. So that's for that part. And then here, I'm going to have a 1/4, and the derivative of this is a -1. Okay, so let's clean this up a little bit. So we've got this 2 cancels a little here, leaves a 2. I've got x over 2 root x squared plus 1 minus 1/4. Okay, so that's t prime. I'm going to be setting this equal to 0, so I would like to actually create a single fraction with this. So I'm going to find a common denominator. So I'm going to multiply this side by the square root of x squared plus 1 over the square root of x squared plus 1. And this side by 2 over 2. I guess I didn't need to cancel that 2 there. And we've got 2x minus the square root of x squared plus 1 in the numerator. The denominator is 4 times the square root of x squared plus 1. And now I need to set this equal to 0. 2x minus the square root of x squared plus 1 equals 0. And we're going to use our calculator for this. Okay, so I typed in my function and I'm going to graph it. And we're looking for the 0. So second calc 0. Oh, that works for a left bound. Move along here for a right bound. And back here for my guess. And looks like we get x is approximately, if I go 3 decimal places, 0.577. And that would be miles along the shore to minimize the time. And it's a good idea then to plug in that value back into your equation for your time. If you do that, you should find that the minimum time is 1.183 hours. So again, that would be plugging back in your value for x into our expression for time. And I suppose we should also verify that this is a minimum and not a maximum, because sometimes that can happen. It doesn't have, often that will be the min or the max might occur on an endpoint. That doesn't apply here. But it's always a good idea to verify that it is a min. So I think I'm going to stop here and you'll have some practice problems to do.